So this brings us to the quantification of exactly how strong a strong acid is or how strong a weak acid is, and the characterization of that quantitatively. So let's look at one of our favorite acid reactions, and that's the reaction of acetic acid with water. And the first thing we notice is that we see this carboxylic group that is characterized by that double oxygen-carbon bond linking into the OH at the end of that molecular structure. And it's the fact that oxygen draws electron density away from that hydrogen that exposes that hydrogen for its transfer as an H plus proton to water. And so we immediately see that the proton donor aspect results from the weak binding of a terminal hydrogen from that molecular structure. And so that reaction, of course, moves forward to produce our H3O+, that's the acidic character of it. And then the acetate anion is exactly the molecular structure we started with, but it's lost an H+ that formed the H3O+. But now comes the interesting aspect of looking at the symmetry between acid and base behavior in this reaction. And this is the Bronsted-Lowry formulation of acid-base reactions. And they defined an acid as a proton donor. So we have acetic acid, but we have something very interesting. We have a conjugate base, which is the acetate anion. So we have an acid and its conjugate base. But look what else we have. We've got a base because it's a proton acceptor in the Bronsted-Lowry formulation, and it reacts to form H3O+ that's an acid because it's a proton donor when the reaction goes back in the opposite direction. So we have this beautiful symmetry between an acid and its conjugate base and a base and its conjugate acid. But we can now write the equilibrium constant for this reaction, and we refer to that as the acid ionization constant. And when I write this expression for the acid ionization constant, you will immediately recognize its form because, in fact, it's simply an equilibrium constant, and we designate that acid ionization constant as K sub A, but we write it in exactly the same form. It's equal to H3O+ in this case, times the concentration of the acetate anion, the C2H3O2-. And we divide that through, neglecting the pure water liquid, we divide that through by the concentration of the acetic acid, HC2H3O2. And so that's very important. That designates our acid ionization constant, and it tells us the character of that acid reaction. If that equilibrium constant is very, very small, and by the way, for acetic acid, that acid ionization constant is 1.8 times 10 to the minus 5. That means it's very small, and that means that the reaction, when it comes to equilibrium, is going to be primarily made up of reactants. That is, the reaction does not shift in large measure to the right, that is, in the production of H3O+. So a small equilibrium constant for an acid ionization reaction means that the reactants, the acid and water, by far dominate the concentrations in that solution. Well, since we've defined an acid ionization constant, we need to define exactly the same functional form for a base. And again, our base is a proton acceptor, or when we think about it, it's a molecule which, placed into water, successfully steals an H+ from water. And as we've said before, ammonia is a very good example of this. It's a fairly weak base. And in that reaction, we form NH4 plus and OH minus. And it's that OH minus that determines the base characteristics of that chemical reaction. Now let's look at the symmetry between a base as a reactant and the resulting conjugate pair acid. So I start with a base, NH3, and I match that up with its conjugate acid as a product. And then I do exactly the same thing. In this case, water is the acid, and when I link it to its conjugate base, that is the hydroxide anion. We can now write the equilibrium constant for a base reaction exactly the same form. We've got the concentration of the products, NH4 plus and OH minus, divided by the concentration of the base, NH3, and that base ionization constant is equal to 1.8 times 10 to the minus 5. Again, very small. So that says that when I put ammonia into water, the dominant form of the nitrogen compound in water is in fact NH3, and only a small fraction forms NH4 plus.